Hi, juniors. Hope you guys had a great Memorial Day weekend. It was nice and warm outside, so hopefully you guys were able to safely get outdoors and get an extra day away from online school. So I don't know if you remember, but there was a unanimous vote to have the next set of notes done pre-recorded. I'm a little hurt. Just kidding. It's actually, I think it's easier to do this pre-recorded. Obviously, the big drawback is questions, don't happen in real time, but it gives more flexibility for you guys. So you can sign on, take these at your convenience. Obviously, if I'm moving too fast, you can pause, go back. I know there is one slide where you have a lot to write down. So it'll be a lot. It'll be 60 slides. I'm covering two sections. Notice I'm going a little out of order. 6.4, which is acid rain, and then 6.3, which is smog. Really no important reason to do that. But this will be it for content. And so if you need to break this up over 2 days, that's fine. But we'll go ahead and get started. 6.4 and 6.3 together are part of the impacts of burning fossil fuels. There's other impacts like climate change. I'd say the biggest impact of burning fossil fuels, but we'll save that until next year because it's such a broad topic that I want to spend more time on. What elements do fossil fuels consist of? And I'll give you guys a hint. Fossil fuels, carbon, coal, oil, gas. That stuff comes from the really the remains of plants and animals from millions of years ago. So think about dinosaurs and trees from millions and millions of years ago. Over time, over pressure and heat and a lot of time, they actually get compressed into fossil fuels. So Josh, I'll give you a chance to redeem yourself. What elements are fossil fuels consistent of? Yep. Yep. You got it. Great job, man. All right. So it's the same exact stuff. And then the last question should be pretty straightforward. Look at a coal burning factory. We are putting the coal in here. We burn the coal to heat water to spin a turbine to create electricity. And we'll get into those details next year as well. But notice the waste gases. So when we burn that coal, all those gases end up in the atmosphere. So the last question, when you burn fossil fuels, what elements get released? I'll give you guys a second to think about that. Pretty easy question. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and a little bit of mercury. So that brings us to this nice little handy acronym. When we burn fossil fuels, CHNOPS are released. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. They all end up in the atmosphere. And then don't forget, you could add a little note, plus mercury. A little bit of mercury. Hg is actually the elemental symbol for mercury. Now, when this stuff goes up into the atmosphere, do you think it just goes its separate ways and it stays independent from one another, or do you think they combine? Nazifa? You got it. Yes, they combine. Very good. Think back to our last unit, guys, 6.2. Ozone and oxygen, O3 and O2, combining, disassociating, recombining. It's going to be similar with this stuff. So this brings us to, in a second, the biggest slide you'll need to write down. The nitrogen and oxygen get together. They make NOx, NOx, which is a shorthand for nitrogen dioxide or nitrogen trioxide. The X means 2 or 3 oxygens. Carbon and oxygen get together to make CO2, obviously one of our main greenhouse gases, then carbon monoxide, which is poisonous. Hydrogen and oxygen get together to make water. Water is a greenhouse gas. Many people don't think of water as trapping heat, but it does. Phosphorus and oxygen get together. Phosphorus pentoxide, it's a solid pollutant. Remember, the phosphorus cycle is never in the atmosphere. Sulfur and oxygen get together to make SOx, SO2 and SO3, sulfur dye and trioxide. Mercury, carbon, and hydrogen get together to make methyl mercury, which is the mercury we learned about in the fall that biomagnifies up the food chain. So take a moment, you can pause the video, but get all this written down. I want you guys to know the element, the raw element that comes from the fossil fuels, how it combines or what it does in the atmosphere, and then lastly, the overall impact on either nature or humans. You don't need to write down the phosphorus pentoxide because that's not actually an atmospheric pollutant. So take a minute, pause the video, get this whole thing written down. Next to acid rain for the sulfur oxides, you can also put down smog as well. Okay, moving on. So we can summarize all the negative impacts of burning fossil fuels really fivefold. Number one, acid rain. Number two, particulates. You've probably never heard that term, but it's pretty straightforward. Particulates are small particles that end up in the air. Smog, which comes from the term smoke and fog. Mercury, and then lastly, the big one, greenhouse gases. So we're just going to go right down through the list, starting with acid rain. And as I mentioned before, we've already learned about mercury in the ecosystem, so we will quickly recap that. But then greenhouse gases is such a major topic, we will save that until senior year. So starting with acid rain, also known as acid deposition, to deposit, meaning for acid to land on something. Chinops produce acid rain when they chemically combine with water in the atmosphere. This is considered a secondary pollutant. The primary pollutant is what comes out of the tailpipe of your car or the smokestack of the coal burning power plant. But when it mixes with something, it could be sunlight, it could be water. I think those are the two common ones, but if it mixes with anything and when it's in the atmosphere, it then becomes a secondary pollutant. So you do need to know that acid rain is considered a secondary pollutant because whatever the pollutant is, usually NOx or SOx, is going to mix with water and make that secondary pollutant. So we get nitric acid when nitrous oxide mixes with water. We get sulfuric acid when sulfuric oxides mix with water. And then lastly, we get carbonic acid, which is when CO2 mixes with water. I do want you guys to know that when we think about acid rain, we really don't worry so much about carbonic acid. It's a weak acid. It's naturally found in the atmosphere. Because of that, lakes and rivers and rainwater tends to be slightly acidic from neutral. But we generally think of NOx and SOx combining with water to make the acid rain that we worry about towards the environment, towards society in terms of making those big impacts. Oh, you should write this down. I remember I added this in last minute. Carbonic acid ends up acidifying the ocean, and even though it is to a small degree, so it's not going to take the pH from 7 down to 3 like the sulfuric acid could, even if it lowers the pH a little bit, there's some pretty fragile ecosystems, coral reefs being a major one, where if that ocean acidifies just a bit, it could harm food webs. So we do need to understand that although carbonic acid is not associated with acid rain, it is often associated with ocean acidification. And as I mentioned, acid deposition to deposit. That simply means the movement from the atmosphere to land. That deposition can be in the form of rain or snow or sleet. Sometimes it can be dry deposition. It can just fall out of the air, as a solid particulate. Another diagram showing the emission source, the NOx or SOx mixing with, oxidizing and depositing as dry, or mixing with water and depositing as wet. Statue in Boston, this is from acid snow. So the snow actually will sit on this statue and eat away, just like any other acid can do. In terms of how acid rain affects ecology or ecosystems, there can be obviously a direct effect. That is when the acid will land on a plant or aquatic organism. Obviously, this is going to be a health effect if the acidic rain is so acidic it can burn, it can cause tissue damage, but much more realistic. So I would say that the indirect effect is going to be much more common. Nutrient leaching in the soil. When soils become acidified, the roots can't grab on to those nutrients as well. In fact, the roots will start sucking up metals out of the soils. And so the metal solubility in organisms increases, which is a bad thing. And then nutrients can leach out of the soil, can't be grabbed by the plants, which is also a bad thing. This is an example of a forest affected by acid rain. You can see that all these tall trees, the mature ecosystem was destroyed. However, acid rain doesn't necessarily harm an ecosystem indefinitely. Think about what you know about succession and secondary succession. A new forest can then start regrowing after that acid rain event has ended. If you look closely here, this is a river. You see all these tiny little silver dots, and if you zoom in on all these tiny little silver dots, they are fish, dead fish. This is considered a fish kill. When there's a species that has a certain tolerance, let's say this species of fish can tolerate a low pH of 5.1, and then all of a sudden, if there's enough acid mine drainage or acid rain and the pH gets down to, I don't know, 4.9 or 5, every fish of this species will get killed. And you might think, well, it's just one species of fish, but knowing what we know about food chains and food webs, everything's interconnected. And so this one species of fish dying could lead to extinctions or population declines or population growth to other species in the same ecosystem. This is important to recognize that acid rain can cross borders. So what we mean by that is that if the state of Ohio, let me outline Ohio, is producing a whole lot of acid rain, that doesn't just harm the state of Ohio. Again, thinking back to ecology, we know that wind on the northern hemisphere and planet Earth generally moves from west to east. So actually, the state of Pennsylvania sued Ohio not too long ago because of the acid rain from the. Anyone know what type of economy Ohio or Cleveland's economy historically was based on? Mia? No. Good try. Milan, put your phone away. Come on, man. Haley, you got it. All right. Yeah, metal smelting and steel making. So the Cleveland factories where we're creating all this acid rain. That acid rain was moving east, landing on Pennsylvania, and it was the Pennsylvania forest that were dealing with the brunt of it. The important thing to recognize is it makes socio-political fights across borders. We see the same thing not just from state to state, but country to country. Germany, a lot of industry, a lot of acid rain. However, Germany doesn't get the worst of it. It's actually heading east. Poland is the one getting the worst of the acid rain from Germany. A little bit of background on the pH scale. It's from 1 to 14. Anything less than 7 is considered an acid. Anything more than 7 is considered a base or an alkaline. 7 is considered neutral. Pure water has a pH of 7. Natural rain, though, if you remember that carbonic acid that's naturally found in the atmosphere, is going to have a slightly lower than neutral pH. So natural rain is considered about 5.5 to 6.5. And then anything less than 5.5 we consider acid rain. Obviously, acid rain can be severe. It can be down to 3 or 4 and actually could burn the skin. It could also be less severe, 5, 5.5. Just so you understand the factor of how acidic acid rain can be, pH is a log scale. And so what that means is that pH of 6 is actually 10 times more acidic than 7. And 5 is 1,000 times more acidic than 7. And 5 is 100 times more acidic than 7. 4 is 1,000 times more acidic than 7. And then last but not least, thinking about how we deal with the issue of acid rain. So I'm going to tell you now that acidity is the measurement of how many free hydrogens are in a solution. So knowing that, how could we buffer acid pH back to a neutral level? All right, and the big hint is that if there's free hydrogens in a solution, that's going to increase the acidity. And also realize this can get confusing. If the acidity goes up, that means the pH goes down. They're indirectly related. So free hydrogens cause acidity. How do we buffer an ecosystem or an acid back to neutral? Well, got to get rid of those free hydrogens. So what we do is we put something in the environment that will grab those free hydrogens. A great example would be clay or some sort of organic material that basically absorbs free hydrogens. And so all these free hydrogens that are causing acidity, they get basically grabbed onto. I'm sure there's a more appropriate chemical term, but they get held onto by what's called a buffer, such as clay or soil. Limestone would be another one. And then by grabbing onto those free hydrogens, it's going to increase the pH, meaning it's going to reduce the acidity. Here's an example of a lake in upstate New York. The lake was affected by acid rain, so environmental managers decided to dump a whole bunch of limestone into the lake. Limestone is a pH buffer. It's a base, but more importantly, it grabs onto free hydrogens in the water. And so by grabbing those free hydrogens, it's going to reduce the acidity. Another picture of a similar lake upstate New York. So this goes to level 3, remediation. Think back to our pollution unit. How do we clean up acid rain? We use pH buffers. I mentioned clay. The picture, I believe, is limestone, and then also calcium carbonate is another common one. Calcium carbonate is pretty much chalk. It's the main ingredient in Tums. If you think about when you have a stomach ache, it's probably because you're dealing with stomach acidity, so you eat a couple Tums, that neutralizes the acid and your stomach feels better. It's basically the same thing here on an environmental scale. One issue to think about though, does this actually remove the original chemical that caused the acidity? Not necessarily. So if there's a bunch of sulfuric acid in the water, yes, we're removing these free hydrogens that are causing the acidity, but we're not necessarily removing the chemical itself. Moving backwards, how do we reduce acid rain? Maybe that's level 2. Scrubbers. Scrubbers are things that go in the inside of a smokestack, and they basically grab onto some of the sulfur and some of the nitrogen before it leaves the smokestack into the atmosphere. Catalytic converters, similar to a scrubber. It's kind of like a scrubber for inside of your car. Cars that have been made since the 80s all have catalytic converters, and it removes some of the SO2 and NO2 before it leaves the tailpipe. And then last but not least, what would be better than reducing the problem? Should be obvious. Correct. Preventing the problem. Pretty obvious. Stop burning coal and other fossil fuels. Remember, coal is pretty much the dirtiest fossil fuel, but any fossil fuel, whether it's oil, gas, or coal, all have the potential to lead to, or not potential, they do lead to acid rain because the sulfur and the nitrogen end up in the atmosphere, they combine with water, and they come back down to Earth. So generating our electricity with things like solar and wind, that's much better than level 2 or 3. Just don't make the acid rain in the first place. Okay, number 2, particulates. So remember, we're looking at the bad stuff that is caused by burning fossil fuels. Number 1, acid rain, and that's 6.4 in your notes. Number 2, particulates. As I mentioned before, it is pollution in a tiny solid or liquid form. Just think of particle, basically. You breathe it in, and it causes asthma, it causes cancers, and it causes respiratory issues. Anyone who lives near a coal plant is going to be at a much greater risk for particulates and the cancers and the asthma that come with it. So this is going to be an example of environmental racism or inequality. If you think about the types of individuals who are likely to live near a coal burning plant, It's going to be minorities. It's going to be those people with less economic opportunity. It's generally not going to be white people. It's not going to be affluent people. Here's an example of pet coke along the Detroit River. This is one of the outputs, like basically a waste product of coal. And there's no regulations about it. And so it just sits in this giant pile next to the Detroit River. Anytime the wind blows, this pet coke, this particulate is just going to end up all throughout the neighborhoods. It's going to get in people's houses. It's going to get in their eyes, their nose, their mouth. Oftentimes it's on the microscopic level, but if you are living around the Detroit River, you are absolutely breathing it in. Coal power plant in River Rouge. Again, this is going to be an example where it is not a high income level area, so the people dealing with the particulates here and the smog and the not acid rain. Sorry, acid rain is more regional, but smog and particulates are very localized. It's going to be whether you live near the petcoke or near the coal power plant. Again, looking at another example in Chicago, we have three main, I guess, socioeconomic parts of the city. The north side is the wealthiest area of the city. The west side is a poor area, and the south side is a poor area. North side is mostly white people. West side is mostly Latinx, and south side is mostly black. And it's not surprising that we see, because of where the coal plants are, because of the inequalities and the systemic environmental racism that occurs, we see that the blood levels of kids are going to be a lot higher in the west side and in the south side compared to the north side. All right, a little bit about particulate size. So particulates are measured in micrograms. Which is worse, larger or smaller particles, and why do you think that? Take a minute to think about this one. Nancy Lee, go for it. Oh, nope, not larger. Good guess, though. Does anyone else have an answer? Phoebe, yes. You are correct. Smaller. Why smaller? You got it. Good job. Anything smaller than 10 is considered hazardous by the EPA, but the smaller particulates are the most dangerous because they can easily sneak into our body. You guys have nose hairs that can keep the big particles out of your body. You have cilia in your lungs that can sort of trap, large particles that get into your breathing pathways. But if there's a really small particulate like PM1, PM2, that stuff's so small it can sneak past your body's defenses, and so it can actually get into past your nose hairs, past your cilia in your lungs, things like that. So obviously 5 is going to be more hazardous than 10, 3 is going to be more hazardous than 5. It's the smaller particles that are actually the worst. All right, next we have smog, officially known as photochemical smog. Again, this is a secondary pollutant. It comes from auto exhaust and coal power plants. Here, the secondary pollutant is, if you think about the term photochemical, photo generally refers to the sun or sunlight. So you have things like nitrous oxides mixing with oxygen, mixing with sunlight. That creates ozone. Now you might be thinking, great, ozone, that keeps us nice and safe from the sun's harmful rays. No, because this is ozone that's happening in the troposphere. Ozone is good up high, bad nearby. So this is ozone that's created in the troposphere, meaning that's where we are. We breathe it in. It causes all sorts of problems. Smog can be caused by a few different chemicals, but generally speaking, ozone is the main factor, the main player in this cause. A little bit more about primary and secondary atmospheric pollutants. Primary is the direct result of fossil fuel combustion. So it's like literally what leaves your tailpipe or what leaves the smokestack. Examples would be volatile organic compounds, carbon monoxide, carbon dioxide, nitrous oxide. Whereas secondary It goes through some sort of reaction in the atmosphere. That reaction is usually from sunlight or water. Examples would be acid rain, smog, in terms of our best examples of secondary pollutants. Little diagram showing the primary pollutants, and then they mix with something, and then they become a secondary pollutant. Good reminder, I think we talked about this during our pollution unit. Pollution can be natural. A volcano is definitely gonna emit pollution when it erupts, but that pollution is a natural source. It's not anthropogenic. 140 million Americans live in areas of unhealthy levels of smog during parts of the year. That's almost half of our population, mostly in urban areas. And there are some geographical factors that determine smog. Um, Number one is obviously auto and industrial pollution. So if you live in a really green city that has all public transportation running on electric, you're going to have less smog. If you live in a place like Detroit or Metro Detroit, where there's really no public transportation, everyone needs to drive, you're going to end up with more smog. Topography, the best example here would be a valley. If you live in some sort of valley, the smog sort of gets trapped within, in between the mountains. Climate, sunny days means that you're going to have more of a chance for that photochemical reaction to take place, meaning you're going to end up with more ozone. And then there's this term that's kind of odd. It seems like an oxymoron. Thermal inversion. So normally, um, cold air sinks and warm air rises, but sometimes warm air will actually stagnate and it'll just sit on top of a city, and then polluted air gets basically stuck underneath it. And so regardless of it's a warm day, when that warm layer of air basically sits on top of a city, you end up with higher levels of tropospheric ozone. And then last but not least, deforestation. If a city is surrounded by trees, even if you're creating smog, the trees will filter out a lot of that smog. But with no trees, you don't have any natural filtration to filter out the troposphere. So the best example of a city that has, I think, all five of these factors, Los Angeles. It's in a valley surrounded by mountains. It's pretty much warm and sunny all the time. There's very few trees. It's pretty much like a desert ecosystem with maybe some palm trees, but really not a lot of trees. A huge population and no public transport. Everyone's got to drive everywhere. So LA is probably the worst city to live in. Historically, it's gotten a little bit better over the past decade or so, but pretty much the worst city to be in terms of smog in this country. Now, across the world, there's much smoggier places. Notice a lot of these places are in NICs, newly industrialized countries. A lot of them are in Asia, where cities tend to be more densely populated. But luckily for us in the United States, we don't have the highest rates of smog in the world. It tends to be in more newly industrialized, densely populated countries. China's been in the news recently because of their smog. Now, luckily, over the past 3, 4 months, there hasn't been smog anywhere because people aren't driving, goods aren't being produced. So at least we've gotten a bit of a break from smog in our urban areas. A little bit of the health effects of or from smog: respiratory infection, asthma, lung cancer, birth defects, eye, nose irritation. And who's at the highest risk? There's generally like 3 or 4 groups of individuals that, not just to smog, but to any sort of harm, these individuals tend to be at a very high risk. Young people, old people, sick people, and pregnant women. All right, and then lastly, mercury. We can go through this pretty quick because we did learn about this in the fall when we learned about ecosystems. So mercury accumulates in the atmosphere due to coal emissions. It falls back down to the earth during precipitation. And then, like all heavy metals, it bioaccumulates within the body, and then that means it biomagnifies up the food chain. When it's consumed, and it's usually from top level fish. So if you're eating something like catfish or salmon, those are like first level predators or herbivores. And so they're going to have very low levels of mercury. But if you eat a top consumer, if you eat tuna or shark or swordfish, something that is at the top of the food chain, all that mercury has biomagnified up the food chain, so it's going to accumulate at really high levels there. Um, and the people that need to be the most careful about it are kids and pregnant women, because it can lead to neurological deficits. An example here of that inverted pyramid, we see this is DDT, so a different pollutant. This is a pesticide, but same result. So we see that DDT is in the water at very, very low levels. It's in the zooplankton at slightly higher levels. It's in the small fish at bigger levels, and then eventually you get to the top predator. In this case, it is an osprey. We see it's in really high levels. So if we were eating this osprey or another top predator, we'd be getting it in really high levels in our system as well. You can look up from the EPA which fish and where you need to be careful with. Um, in the Great Lakes, because we have a lot of coal burning factories, we need to be fairly careful. So if you're someone that fishes, you should look up the body of water that you fish in, the type of fish that you're eating, and how often you should be eating that fish. Because there's some place, like I don't know where this is, but Lake Nesmith, you should be never eating fish out of there. And so again, if you're eating local fish or catching local fish, you definitely need to be careful about how often and what species of fish you are eating. All right, and then last but not least, greenhouse gases. We will go in depth next topic. No, sorry, that's for seniors. Next spring, we will go in greenhouse gases. So you can jot it down now. Know that it's a big deal. It's probably the biggest environmental issue, or maybe even the biggest issue, to your generation. The main cause is from burning fossil fuels. But again, we'll get into that in much more depth later on. The last thing I want you guys to jot down is pollution management. Just remember those 3 levels of pollution management. They come into play for smog, for acid rain, for any sort of pollution. Less fossil fuels is the obvious one. Make polluters pay. So carbon tax or government regulations. If you run a company on coal, you should pay more money. If you run a company on solar or wind, maybe you should get money back, or you should pay less money. Because right now the costs are externalized. Basically, if you are a polluter, you're making other people sick. You're harming the planet. You're causing asthma and cancer, but you're not the one paying for it. Smarter cars, things like higher fuel standards, catalytic converters, electric cars, and then lastly, reforestation. More trees because they're going to absorb that pollution. They're going to absorb the CO2. In fact, the IB term, which I've never really heard of outside of IB, but you guys should know it, afforestation. So jot that down. Again, everywhere else on Earth, I've heard it called reforestation, but in the world of IB, if you want to sound fancy, like when you're working on your IA, call it afforestation or afforestation. Okay, that's it. I know that was a lot, but hopefully you guys were able to break it down, and have a good weekend. See you next week.